Time doesn't tick the same everywhere under extreme gravity, it slows down. A new study confirms Einstein's prediction. In simulated environments mimicking neutron stars, time can move up to 9% slower for humans compared to normal Earth conditions. Gravity's grip on time. How Einstein's theory of relativity is reshaping our understanding of reality. It sounds like science fiction, but it's pure physics. A groundbreaking study has revealed that time can move up to 9% slower for humans in high-gravity environments. This isn't a metaphor or a poetic exaggeration, it's a measurable scientific reality rooted in Albert Einstein's theory of general relativity. The implications are profound. Time is not a universal constant. It bends, stretches, and warps depending on where you are and how much gravity surrounds you. This phenomenon, known as gravitational time dilation, occurs when intense gravitational fields distort the fabric of spacetime, near massive celestial bodies like neutron stars or black holes. Time itself slows down, and while we can't naturally experience these conditions on Earth, scientists have simulated them in laboratory settings, confirming that time can indeed move significantly slower, up to 9% in extreme gravity zones. Einstein's prediction, time is relative. Albert Einstein first introduced the concept of time dilation in his general theory of relativity in 1915. He proposed that gravity isn't just a force, it is a curvature of spacetime caused by mass. The more massive an object, the more it bends spacetime around it. And this bending affects how time flows. In simple terms, the stronger the gravitational field, the slower time passes. This means that a clock placed near a massive object will tick more slowly than a clock placed farther away. Einstein's equations predicted this effect. But it took decades for technology to catch up and measure it, measuring time dilation on Earth. While we can't naturally experience neutron star gravity on Earth, scientists have found clever ways to test Einstein's theory using atomic clocks, the most precise timekeeping devices ever created. These clocks are so accurate they can detect time differences of billionths of a second. In one famous experiment, researchers placed atomic clocks at different altitudes, one on the ground and one on a tall building. Even with just a few feet of elevation difference, the clocks ticked at slightly different speeds. The higher clock, farther from Earth's gravitational pull, ticked faster than the lower one. These experiments confirmed that gravitational time dilation is real, even in everyday conditions. But what happens when gravity becomes extreme? Simulating neutron star gravity. To explore more dramatic effects, scientists created simulations that mimic the gravitational fields of neutron stars, ultra-dense remnants of collapsed stars. A neutron star packs more mass than our Sun into a sphere just 20 kilometers wide. The gravity on its surface is so intense that it bends light and warps time. In these simulations, researchers found that time could move up to 9% slower compared to normal Earth conditions. That means for every hour experienced near the simulated neutron star surface, 66 minutes would pass in the outside world. This isn't just a theoretical curiosity, it is a glimpse into how time behaves in the universe's most extreme environments. Implications for space travel. Gravitational time dilation has profound implications for astronauts and space explorers. Imagine a crew orbiting a massive planet or approaching the event horizon of a black hole. Time for them would slow down relative to people on Earth. If they spend a few hours near the black hole, days or even weeks could pass back home. This concept was famously dramatized in the film Interstellar, where astronauts visiting a planet near a black hole experienced time at a drastically slower rate. While the movie took artistic liberties, the underlying physics is sound. Einstein's equations support the idea that where you are affects when you are. Biological time. What happens to the human body if time slows down in high-gravity environments? What does that mean for the human body? In theory, biological processes would also slow down. Your heart would beat more slowly, your cells would age more slowly, and your perception of time would remain unchanged. You wouldn't feel the difference, but the outside world would. This raises fascinating questions about aging and longevity. Could astronauts living near massive celestial bodies age more slowly than people on Earth? Could time dilation be harnessed for medical or technological purposes? While these ideas remain speculative, they open new avenues for research and imagination. Philosophical reflections. What is time? The discovery that time can move 9% slower under extreme gravity challenges our most basic assumptions. We often think of time as a constant, a ticking clock that marches forward uniformly. But Einstein showed that time is relative, shaped by motion and gravity. This realization forces us to rethink our place in the universe. Time is not something we move through, it's something that moves with us. It bends around stars, stretches near black holes, and flows differently depending on our position and velocity. In this sense, time is a dimension, not a measurement. It's part of the fabric of reality, woven together with space into the mysterious tapestry of spacetime. Future research. What's next? Scientists continue to explore the boundaries of time dilation. New experiments with quantum clocks, gravitational wave detectors, and space-based observatories are pushing the limits of precision. Researchers hope to study time dilation near white dwarfs, black holes, and even in artificial gravity environments. One exciting possibility is using time dilation to test the unification of general relativity and quantum mechanics, the holy grail of physics. By observing how time behaves at the smallest and largest scales, scientists may uncover clues to the nature of reality itself. Practical applications, GPS and beyond. Gravitational time dilation isn't just a theoretical concept, it has practical applications. The Global Positioning System (GPS) relies on satellites orbiting Earth. These satellites experience slightly weaker gravity than people on the ground, so their clocks tick faster. To maintain accuracy, GPS systems must account for both gravitational and velocity-based time dilation. Without these corrections, GPS would drift by several kilometers each day. This is a powerful example of Einstein's theory at work in everyday life.